Welcome, everyone, to a new episode of the AI Safety Paper Digest podcast.
Great to be here.
Today, we're diving into, well, a really crucial area for the future of autonomous vehicles. How we truly test their safety and robustness, when things get weird.
Yeah, it's a fundamental challenge. Keeps a lot of us AI security folks up at night, I think.
Absolutely.
Right. So while AVs, autonomous vehicles, are getting incredibly capable in, let's say, normal driving.
Right, the day-to-day stuff.
Exactly. The real stress test happens in those rare, high-risk, what we call safety-critical scenarios.
The edge cases.
Those are the ones. The unexpected moves by other drivers that could, lead to a crash. The kind of tricky situations that are hard to predict, even harder to plan for.
And here's the real kicker, isn't it? These scenarios are incredibly difficult and frankly expensive to just find in real-world driving data.
Oh, absolutely. They just don't happen often enough naturally.
Right. So you can't build a good data set.
Precisely. Not for really robust testing. So the paper we're unpacking today, LDCN, LLM-Guided Diffusion for Controllable Generation of Adversarial Safety-Critical Driving Scenarios, well, it offers a pretty fascinating solution.
LDCN. Okay.
Yeah, this work introduces a framework that integrates large language models, LLMs, that with latent diffusion models, LDMs, specifically to generate these tricky scenarios.
Okay, bringing the latest AI tools together.
Exactly. And what's really exciting, especially for, those of us in AI security, is how user-friendly it is. And the fine-grained control, it lets users customize scenarios just using natural language.
So you can just type what you want.
Pretty much. You can tell the AI, basically in plain English, I want this kind of dangerous event.
Yeah.
And it tries to build it for you in the simulation.
Wow. Okay, that moves beyond just describing the theory.
Right. It's getting into concrete, hands-on application, which is great to see.
So let's unpack that a bit. If finding these extreme situations in the real world is, well, almost impossible.
Yeah, practically speaking.
Then simulation is really our main path forward, isn't it?
It has to be.
But what makes simulating these black swan driving events so challenging to get right? Why haven't we nailed this already?
Well, the core issue, like you said, is AVs do well in common situations, the 99%.
Right.
But they're often really under-tested in those rare hazardous cases, the 1% or even less.
And real-world testing is just too expensive.
Prohibitively so.
Yeah.
And collecting enough diverse, high-risk data that covers all the possibilities, it's just near impossible. Think about it. You can't just wait by the roadside hoping for a specific kind of near miss to happen.
Right, not feasible. And previous simulation methods had their own problems.
They did. Historically, manual design using simulators like Carle or Sumo.
Standard tools.
Yeah, standard tools, but they required deep domain expertise. You needed to be a traffic simulation guru.
Okay.
And often the scenarios felt a bit artificial, not quite realistic.
Right, and then came optimization methods.
Yes, things like AdveSim or Strive. They improved realism, definitely, by using large data sets, but they still struggled with efficiency. And critically, that fine-grained control over specific adversarial behaviors was still lacking.
So you could maybe make a crash happen, but not necessarily the exact kind you wanted to test, like a specific aggressive lane change.
Exactly. It was hard to dictate how it happened. And even diffusion models, which, have been amazing for controllable generation in images.
Yeah, huge progress there.
They faced hurdles when applied to traffic simulation.
How so?
Well, previous diffusion approaches for traffic, like diffuser or SafeSim, often meant you had to retrain classifiers or redesign objective functions for every different adversarial strategy you wanted.
So not very flexible.
Not at all. It limited flexibility, user-friendliness. It demanded specialized knowledge for each new kind of attack, basically.
So the key challenges were realism, precise control, and making it usable without needing a PhD in traffic modeling.
You nailed it. Realism, control, usability, that's the trifecta they're aiming for.
Okay, so this is where LDCN comes in, riding the wave of recent generative AI, especially LLMs. How does it tackle these challenges at a high level? What's the core idea?
Right. So LDCN integrates the LLMs and the latent diffusion models, the LDMs.
Okay.
The LLMs provide that natural language interface, right? And their powerful code generation abilities.
Which we've seen explode recently.
Exactly. While the LDMs are really good at modeling complex, realistic driving trajectory distributions, so they handle the making it look real part.
So the LLM understands the what, from the user, and the LDM figures out the how in a realistic way.
That's a great way to put it, yeah. The LLM understands the intent, the LDM makes it happen plausibly.
Okay, cool. And for our listeners who like the technical details, let's talk problem formulation. What's LDC actually trying to optimize for?
Okay, so the core objective is generating multi-agent future trajectories, so predicting where everyone's going.
Right.
Within these scenarios, one vehicle gets tagged as the adversarial vehicle.
The troublemaker.
The troublemaker, exactly. And the goal is to encourage this adversarial vehicle to cause a collision with a rule-based ego vehicle, the one we're testing.
While keeping everyone else sensible?
Critically, yes.
Yeah.
Ensuring all other non-adversarial vehicles behave realistically. No random chaos.
Got it.
And the key part, the user can customize it. Specify the adversarial vehicle, the type of collision, even the intensity.
Intensity, like how aggressive?
Yeah, weak, medium, strong. All through natural language. You can literally type something like, make car #3 perform a high-speed cut-in collision on the ego.
That is really specific control.
Okay, let's unpack the architecture. Two main parts. The Latent Diffusion Model and the LLM Guidance Module. Can you walk us through the LDM part first? How does it generate realistic scenarios?
Absolutely. So unlike some older methods that work directly on like raw trajectory coordinates, LDC's LDM operates in a latent space.
Okay, a compressed representation. Exactly. Think of it as a more efficient summary of the driving scene. This is key for reducing computational load, but also, interestingly, for boosting the expressiveness of the generation.
How so?
Well, it integrates a pre-trained graph-based variational autoencoder, a VAE.
Right. VAEs are good at learning compact representation.
Precisely. And this VAE learns compact representations of how agents interact. That's crucial.
So it's not just random movements, it's learning the social dynamics of driving almost.
That's a good way to think about it, yeah.
All right.
Realistic interactions. The LDM itself uses two GNN-based encoders graph neural networks.
Good for relationships like roads and cars.
Exactly. Capturing past and future scene info, agent interactions. Then there's a learnable UNet for denoising in that latent space, and importantly, an autoregressive trajectory decoder.
Okay.
And that decoder uses a kinematic bicycle model.
Ah, so physics constraints.
Right, keeps it physically plausible. Cars don't teleport or turn on a dime unrealistically.
Ah.
And for inference, when generating, they use DDIM sampling.
Speed up.
Yeah, denoising diffusion implicit models. It lets them skip some intermediate denoising steps, making generation faster without much quality loss.
Okay, makes sense. Now, the LLM guidance module, this sounds like the really novel part, the natural language control. How does my simple query, like cause a sideswipe, turn into a complex driving scenario?
This is where it gets, well, really clever.
Yeah.
LLM acts as this powerful translator or bridge.
Okay.
Your natural language query, like the adversarial vehicle overtakes and collides with the ego vehicle, gets fed in. The LLM, which has been given a structured system prompt to guide it.
So it knows the context.
Right. It then generates Python code, specifically code for a loss function.
Wow. Okay. It writes code.
It writes code. And that loss function then becomes the guidance for the LDM during scenario generation. It tells the LDM what specific outcome to aim for.
So the LLM is essentially writing the adversarial objective function dynamically.
Precisely. That's the core mechanism. And it uses chain of thought, Subot reasoning.
To break down the problem.
Exactly. Helps it decompose the request and generate more complex, nuanced guidance. Better than just simple keyword matching.
Makes sense.
So 3 key steps in this LLM module. First, it interprets your query to figure out the adversarial level. Weak, medium, or strong.
Based on keywords.
Yeah, keywords like aggressive, forceful, high speed would point towards strong.
And that level changes the output.
It does. Step 2 is determining the right loss weights based on that level. Stronger levels get higher weights, pushing the LDM harder towards the adversarial goal.
Controls the intensity.
Controls the intensity, yes. And finally, step 3, it generates the actual Python code for that guidance loss function. It fills in a predefined template using examples of known loss types, like agent collision loss or map collision loss.
This is fascinating. So it's not just cause a collision, it's crafting a specific loss to guide, say, a high-speed overtake or a sharp turn into a collision. Can you give a concrete example? How does normal collision differ from high-speed collision in the generated code?
Okay, yeah. So if you just ask for a normal collision, the LLM might generate a loss function that mainly focuses on minimizing the distance between the ego and adversarial vehicles. Simple proximity.
Makes sense.
But if you add at high speed, the LLM adds another term to that loss function. An additional piece of code specifically designed to encourage high velocity in the adversarial vehicle while it minimizes distance.
Ah, so it combines objectives.
Exactly. Or if you say suddenly turns to cause a collision, it incorporates a turn-related loss, maybe penalizing deviation from a straight path until the last moment, then rewarding a sharp turn angle towards the ego.
That dynamic code generation is.
Yeah.
Yeah, that's a big step up in control.
It really is. It allows for very targeted testing.
But okay, let's be realistic. LLMs generating code. That's not always perfect, right? Code can have bugs. How does LDCine handle that?
Especially for safety testing, you need reliable scenarios.
That's a critical question, and they have an answer. An LLM-based code debugger. A debugger for the generated guidance code.
Exactly. It's a closed-loop system. It takes the generated guidance loss function code and runs a unit test on it.
Yeah.
If there's an error, a syntax error, runtime error, whatever, the debugger gets the code and the error message back.
And tries to fix it.
Yes, it iteratively refines the code, asks the LLM to fix it based on the error until the unit test passes.
So it self-corrects the adversarial objectives.
Pretty much. It significantly boosts the reliability and stability of the guidance functions. Much less manual debugging needed.
That sounds essential. Okay, so once you have this validated guidance loss function, what happens next? How does it guide the overall generation?
Right, so that validated loss function is used to, let's say, nudge or perturb the LDM's denoising process at each step. But the overall objective function guiding the generation has three main parts.
3 parts. Okay, break those down.
Sure. First, there's a loss to make sure the non-adversarial vehicles keep behaving realistically. Stay on the road, don't crash into each other, keeps the background normal.
Maintains realism. Got it.
Second, a loss for the adversarial vehicle itself, also ensuring its behavior stays plausible overall. Like, it shouldn't randomly collide with other background cars or fly off the road unless that's part of the intended adversarial action.
So, constrain the chaos a bit.
Yeah, keep it focused. And the third component is
The LLM-generated adversarial objective we just talked about.
Exactly. That's the driving force, the part that directly controls the adversarial vehicle to induce that specific collision with the ego based on your natural language request.
And how does it define collision mathematically?
It uses standard definitions, like collision penalties based on the Euclidean distance between vehicle centers getting smaller than the sum of their radii, basically. And map collision penalties based on distance to non-drivable areas.
Yeah.
Pretty standard stuff, but applied dynamically via the LLM's generated loss.
Okay, that makes sense. So let's talk results. They tested this on the new scenes data set, right? 1,000 urban scenes. What did they measure?
They focused on three main things: adversariality, behavior plausibility, and efficiency.
Okay, adversariality is.
Yeah.
How good is it at causing trouble?
Basically, yeah. Metrics like the adver-ego collision rate, how often does the adversarial vehicle actually hit the ego? And adversarial acceleration, how aggressive are the maneuvers?
And plausibility.
That's about realism. Things like off-road rates for both adversarial and non-adversarial vehicles, and rates of collisions not involving the ego car. You want the target collision, but not unrealistic side effects.
Right, and efficiency is just speed.
Simulation time, yeah. How fast can it generate these scenarios?
So how did LD-Scene stack up against the competition? AdvSims, Drive, DiffScene, SafeSim.
It performed really well, significantly better in many aspects. For instance, its adver-ego collision rate was 40.75%.
Okay. Is that high compared to others?
Very much so. The next best baseline, SafeSim, was down at 27.81%. So LD-Scene was substantially better at actually generating the intended adversarial collisions.
Wow, big difference. And did it maintain realism?
It did. Crucially, its adversarial off-road rate was relatively low, around 12.52%. This suggests the generated scenarios are aggressive, yes, but still mostly physically feasible within the road limits.
So, effective and plausible.
Exactly. And it was efficient, too, much faster than the optimization-based methods like AdSim that need costly test time optimization.
The paper shows some visualizations, examples of generated scenarios. What really jumps out from those?
What's really striking are the specific types of scenarios it creates. You see complex cut-ins, tricky interactions at junctions, U-turns leading to conflict, even counterflow driving or issues in roundabouts.
These aren't just simple rear ends.
Not at all. They're nuanced, challenging situations designed to stress test specific AV decision-making logic. Like, how does the AV handle someone violating traffic rules? Or make a critical yield or pass decision? These are exactly the kinds of things that are incredibly hard to find reliably in the real world.
And the ablation studies, where they tested removing parts of the system, how important was that code debugger you mentioned?
Oh, it was pivotal, absolutely critical for robustness. The results showed the debugger significantly improved the success rate of actually executing the LLM-generated guidance code.
By how much?
Well, for GPT-4o, the success rate jumped from about 69% without the debugger to 95% with it.
95%, that's huge.
It's a massive improvement in reliability, and it achieved this at a reasonable computational overhead. It means researchers can actually trust the system to work most of the time without constant manual fixes.
That makes it practical. Okay, finally, the controllability studies. This is where the natural language part really proves its worth, right?
Indeed. They explicitly tested controlling the intensity. They showed LDCine could understand queries aiming for weak, medium, or strong adversarial levels.
And the scenarios reflected that.
Yes. Strong queries consistently led to scenarios with shorter time to collision, TTC values, and higher adversarial accelerations. More aggressive, more dangerous maneuvers, just as requested.
Beyond just intensity, it could control specific types of behavior.
Yes, this is maybe the most powerful demonstration we touched on it, but generating a specific loss function for, say, a high-speed overtaking collision versus a sharp turn collision, just based on the text request, that's transformative for targeted testing.
Can you give an example again of how that looks in the simulation?
Sure. For the high-speed overtake, the system might generate a scenario where the adversarial car accelerates significantly in the adjacent lane before cutting in front of the ego vehicle to cause the collision. It simulates that really reckless high-speed pass.
Right.
For the sharp turn, it might generate a vehicle following its lane normally, then suddenly swerving abruptly off its path directly towards the ego, testing immediate reaction times. That level of specific behavioral control is key.
So summing it all up, LD Scene seems like a really powerful, quite user-friendly and impressively controllable way to generate these vital adversarial scenarios for AV testing.
I think that's fair to say. It balances the need for realism, which is crucial, with the ability to induce specific, challenging behaviors that you really need to test.
And it lowers the barrier to entry.
Exactly. By integrating LLMs and LDMs this way, it offers a flexible path for users, even if they aren't deep experts in traffic simulation or control theory, to create these custom, high-impact test cases.
The COT reasoning and the debugger really help there too, making it more robust.
Definitely. They bolster reliability and effectiveness significantly. This capability to synthesize realistic, targeted adversarial events, it's just crucial for rigorously evaluating AV performance and finding vulnerabilities before deployment.
It really feels like a step forward in how we do adversarial scenario generation.
I agree. It moves the needle on proactive safety validation.
So as we wrap up, it leaves us thinking, with this kind of precise natural language control over simulated danger, what new frontiers does this open up for AV testing? And maybe more philosophically, what are the ethical considerations as we get better at making AI create intelligent adversarial situations for other AIs? Something to ponder. Well, thank you for joining us on this episode of AI Safety Paper Digest. We hope you found this discussion on LD Scene insightful.
Yeah, fascinating paper. We look forward to exploring more cutting-edge research with you all next time.